All right, I think that's our cue to start. So we'll kick off where we left off last time, but before we get into more about point defects, a quick correction. I noticed after I gave you the slides and went through the presentation last time that I had these numbers backwards. So when you're looking at the spinel, there's actually twice as many 6-fold coordinated sites as 4-fold. I don't know how I screwed that up, but just wanted to give you a heads up that if you're going to use these slides as a reference in some way, please go back and fix that. Pretty hopefully pretty minor, but when it comes to the magnetic doping and tweaking magnetic properties of spinels, that ends up being really important because it's shifting the cations on which one of those coordinations that drives a lot of the fun in the magnetic space. So we'll move on to point defects. We got started last time we went through stoichiometric point defects. So this is Frankel, Schottky, and then electron hole pairs. And now we get to get into the fun stuff. So we can actually introduce non-stoichiometric point defects. So these are things that are going to have to be compensated in some way. That might be electronically, so using electrons and holes. It might be with other defects, so vacancies or interstitials or these kinds of things. And importantly, this can be intentional. So you might want to do this, or it can be unintentional. It might be in a contaminant that you had no idea was around. It doesn't really matter. It happens. And so we need to understand how these kinds of defects are compensated, what that means in terms of the properties. So as you might imagine, if you introduce a defect that brings along with it compensating electronic carriers, that can change the electrical behavior significantly. And we talked last time about how electrical conductivity can change by 30 or 40 orders of magnitude. This is one way to engineer that, is by tweaking the density of those carriers. So we'll jump into these point defects. So I'm just going to use an example of aluminum doped magnesia. Nobody's ever going to want to do this, but it's just a simple example to show you the concepts. So we're going to stick aluminum into magnesium oxide. So that doesn't mean we're introducing aluminum metal. We're going to introduce the aluminum as an oxide when it goes into magnesium oxide for simplicity. That's more relevant if you were to do this in the lab. But keep in mind that when we talked last time about the way that we treat these defects, we assume that they are dilute and non-interacting. And so we're going to continue with that process, even though we may be introducing 20% or massive amounts. And this is where the terminology, a lot of times we're lazy with the terminology and still call that doping. It's really more alloying or solid solution or other types of phrasing that would be more appropriate. But like I said, we're often lazy and just use the word doping. The semiconductor crowd laughs at us because to them, doping is changing things by parts per million. But as long as we know what we're talking about, I think the terminology is less important as long as you can convey it. So we've got a couple of different options for putting aluminum into magnesium oxide. So aluminum is a 3+ cation going in, replacing a 2+ cation. How do you compensate that? So one possibility is that it's ionically compensated. So that simply means that if when you put a 3+ on a 2+ site, you've got an extra positive charge around somehow. So if it's ionically compensated, that just means that you're using ions to compensate for that charge. Very, very simple. Electronically, you're using electronic charge carriers, so electrons or holes. There's no right or wrong. There's no, this one is always going to happen and this one's never going to happen. The way that we do this is, okay, it's a thought experiment. If I put aluminum into magnesium oxide, as I've got drawn here, and it is ionically compensated by forming magnesium vacancies, what would that look like? And then we do the thought experiment for the alternative option. Well, I put alumina into magnesium oxide. So that's aluminum sitting on the magnesium site, and it's electronically compensated. So in this case, I've got 2 electrons that are compensating for the extra positive, the effective positive charges of the aluminum sitting on the magnesium site. Then how do I compensate for that? Electronically, that means that I have 2 oxygens are coming from the alumina. That's represented here. But if you remember the site balance aspect that we had when we talked about the stoichiometric defects, because it's magnesium oxide in the lattice, so we've just got MgO, MgO, we throw in a couple of aluminums, we still have to have one anion for one cation because the overall lattice is MgO. So that means we've got two magnesium sites taken care of, two oxygen sites taken care of, but from a mass perspective, there's an extra aluminum or an extra oxygen that came along with the aluminum. Where does it go? There's no place for it to sit in the lattice. So it goes away as a gas. Hopefully that makes sense from a balancing the chemistry perspective. What does that mean in terms of the actual behavior of the material? So when we go back to the chemical reaction, the equilibrium rate constant that we talked about last time, we can do products over reactants just like we did before. The products that we have to deal with are aluminum on the magnesium site. There's two of them, so that's squared. The concentration of electrons, that should actually be squared. And then the oxygen, the contribution of oxygen to this goes with the partial pressure. So that gives us a partial pressure dependence of this reactivity. If you remember chemistry, again, we've got Le Chatelier's principle. So that means that if we put extra, let's say in this case, we put extra oxygen into the atmosphere, that's going to push the reaction back that way because there's too much of this product and it's going to push the reaction to go in reverse. In that case, that would be precipitating out aluminum oxide. If we remove that oxygen, then if we remove oxygen from the atmosphere and lower the overall partial pressure, that's going to push the reaction this direction and lead it to happen more easily. So we say that sort of flippantly as if, oh, I'm just going to take oxygen and take oxygen out and it's going to drive this reaction, this kind of thing. It's kind of a chicken egg thing. So when we're in this particular case where we're talking about, for example, doping magnesium oxide with alumina, yes, you would release oxygen during that reaction. So that would be the chemical reaction of actually getting these mixing, not necessarily the sintering process. So, but keep in mind, during the sintering process, and we'll talk about this, hopefully we get to it later today. During the sintering process, if you've already done calcination, the chemistry is finished, and the sintering portion is just the physical reactions without the chemistry occurring. And so whenever whatever chemistry that we're representing with these equations is happening whenever that reaction is occurring. But again, we can sort of tweak this during the sintering process, during post-processing, that kind of thing. We'll get to that a bit later on. I want to walk through the equations first, and then hopefully you'll see why they matter as we get along. The other piece that's important to this is once we've gone through the rate equation, we can also look at electron neutrality, and we just know because all of the positive charges have to equal all of the negative charges, that we get just as many electrons as we get aluminum sitting on a magnesium site. So that makes sense. Hopefully that makes sense. So that's for the electronic compensation. If we go back to the ionic compensation, this is a scenario where we've got a couple of aluminums sitting on magnesium sites. For every pair of those replacements, we can compensate for that charge with just one missing magnesium. And so if we have that same magnesium oxygen lattice, and then we yank out two of those magnesiums and put in two aluminums, now we're actually taking out a third magnesium, and this becomes a vacancy. That one becomes aluminum, that becomes aluminum, but we brought three oxygens along with that aluminum, so all of the sites are still filled. That should be 3. I will fix these slides and update the PDF. So apologies for that. Hopefully you guys are tracking along and correcting my mistakes as we go. Same sort of scenario from the rate constant. We've got the aluminum sitting on the magnesium site squared because there's 2 of those times the concentration of magnesium vacancies. And then when we look at the electron neutrality, a lot of times people will get confused by this because it looks like you've got twice as many charges here. But remember, what we are trying to do, what we're doing is stating that all of the negative charges sum up to equal all of the positive charges. And these brackets represent concentration. So all this is saying is that because each magnesium vacancy counts as a 2 minus, then we need twice as many aluminum on magnesium site defects as we need magnesium vacancy defects to balance out. So this just means that there's half as many magnesium vacancies as there are aluminum on magnesium sites because we're comparing the concentrations in this last equation. So that can be confusing to people a lot of times. Just step back, and if you have to, go through a quick just example. So if I had 5 magnesium vacancies, that would be a total of 10 negative charges. And so that would give me 10 aluminum on magnesium sites for 5 magnesium vacancies. It works out. It looks confusing, but hopefully it's straightforward. That's the nomenclature. I'm not going to go into a huge amount of detail on this. I'm not going to walk you through too many examples because this may not be something that everyone is excited about. But I did upload a PDF that goes into a lot more detail that you can use as a reference. It's on the Dropbox site. Please check that out. If people are interested in this, let me know. We can go into a ton more detail. This ends up being really, really useful. So I want to just scratch the surface and I'll show you how it can be useful, and then you can dig into more details on your own systems. Or shoot me an email, send me something in the chat about a specific question, and then we can go into that in more detail. So this is one example of what would happen in aluminum-doped magnesium oxide. It's just one example, though. So for ionic compensation, I'm by definition saying that I'm sticking aluminum on the magnesium site. So that's this aluminum on a magnesium site. Simply saying that it's ionically compensated, there are several different ways that could happen. That could be a magnesium vacancy. That's what we've already talked about. What else could it be? What else would compensate for this positive charge, the effective positive charge of sticking aluminum on a magnesium site? I could have an oxygen interstitial. Hopefully that makes some people cringe. Because if you think about the magnesium oxide crystal structure, it's already almost close packed. So shoving an oxygen into a site where it's not going to fit seems like it would be really high energy. And so we often ignore oxygen interstitials as a possibility because just from a geometric perspective, they end up being very high energy. But they're possible. And they always happen, but they happen at very low concentrations for the most part. So we a lot of times ignore those, but they just keep in mind that they're possible. And so we can do a ton of different possibilities of just thought experiments for these defect compensation reactions. It takes understanding the thermodynamic energetic costs of each one of these to know which one is going to dominate under different conditions. And that's where we'll eventually get to, is trying to understand how to compare those. Can you increase oxygen interstitial concentration with quenching? So it's not just the oxygen interstitial concentration you can increase with quenching. All of these defects are going to have, well, almost always, the defect concentration is going to be higher at higher temperatures, just because there's more energy available. So you've got more possibility of energetic things happening. So that's true of Schottky defects, that's true of Frankel defects, and it's a little bit less true for these kinds of doping situations, because I mentioned before that this example where you could actually drive the reaction back and forth by changing the PO2. In this case, we're sort of setting the defect concentration by how much alumina we put in the first place. And if we're in a situation where all of the alumina that we put in is going to be dissolved and lead to some sort of a defect, then we know that it's got to be either compensated ionically or electronically. So it's going to be a different balance of these two. And so the balance of which defect compensation mechanism dominates is what will vary with temperature and with the energies of the different species. So generally we look at at least for these kinds of scenarios where we're talking about doping a material with a different chemistry, or we've got impurities that are causing these kinds of defects and compensations. We generally look at that defect, the initial dopant concentration, as the independent variable, because it's already there. We don't know where it came from, or we put in a specified amount. That's just there, and then we increase the temperature, or we go through this reaction, whatever the situation is, and we end up having these kinds of species that are compensating for it. But you're right. If you sort of flip things around, and if you're sitting at a boundary where I mentioned before this potential solubility limit, maybe it's more soluble at high temperatures, and then you can quench and keep things in that high temperature state, or you can slowly cool down and precipitate out a second phase, and you can accelerate that or slow it down by changing PO2 if this is the scenario. So again, tons of hypotheticals here, but it's really the thinking about the mechanisms along the way, because every situation is going to be different. It is always possible to do one of these things. The question is making the thing that you're trying to do the low energy state. And so one last point on that quenching question. Quenching is a relative term. So quenching really just means you cool this down. You sort of, the concept is you equilibrate at a certain temperature, at high temperature of some sort, and then you cool it fast enough that whatever reaction that you're talking about can't happen. So the kinetics determine how fast that quench rate has to be. Maybe that quench rate is you pull it out of the furnace and shove it into water, and that's quenching. Maybe you cool it down over the course of 2 days. But the kinetics of whatever process that was are still so slow that you never get to equilibrium. So you've frozen in that higher temperature state. If that kind of thing weren't the case, then we wouldn't have glasses, right? So there are a bunch of different ways that you can kinetically hinder something and essentially quench it. And so keep in mind that a lot of times we will sinter things at 1200, 1400 C, and then we'll cool them down. It doesn't really matter how fast we cool them down in an absolute scale. It is relative to whatever processes that we care about. Was that cooling rate fast enough to freeze in whatever happened at high temperature for defect compensation? A lot of times it is. A lot of times the kinetics of re-equilibrating to PO2 or to defect distributions or whatever, those kinetics can be really, really slow. And so maybe you've quenched in the Schottky concentration that represents equilibrium at your sintering temperature. And you have to keep that in mind when you go back and make electrical measurements later. Any measurements, but particularly electrical, because they end up being so sensitive. All right, so another example. And this, I'm intentionally choosing an example that strangely doesn't happen very often. So we will go with TiO2, and then I'll tell you what I mean by it doesn't happen very often after we go through it. So we are going to start off with, we're going to talk about oxygen vacancies. So just by the naming of the problem, we're saying oxygen vacancies are the dominant defect. How are they going to be compensated in this situation? So if we've got titania, TiO2, we've got oxygen vacancies that are effective 2+ charges. How can I compensate for those? If it's ionic compensation, then what would compensate for an oxygen vacancy? Well, it could be an oxygen interstitial, which would be effective 2 negative charge. We've already discussed how those are usually really high energy. So maybe that's not the case. Maybe it is. What else could we have? We could also have titanium vacancies. So that would be effective 4-. Any other suggestions of what could ionically compensate for an oxygen vacancy in titanium? We've only got 2 ions, so that's really it from an ionic perspective. Electronic, we only have 2 options there. We've got electrons or we've got holes. Or we can change the valence of the titanium. So we will go through the example of pretending that titanium stays 4+, and then we'll come back and look at what would happen if we change the titanium valence. So one option for ionic compensation is we've got oxygen vacancies, And then we just have, for every 2 oxygen vacancies, we have 1 titanium vacancy. And all we did was just remove 1 formula unit from that infinite lattice that is our baseline. So just like we did when Schottky defects, we start with the baseline, everything is perfect. We pull out a stoichiometric number of vacancies, ta-da, that's a Schottky defect. That's really all this is. So ionic compensation often ends up being either Schottky or Frenkel. So if we were to compensate with an oxygen interstitial, that would just be an anionic Frenkel defect. They're just special names for the same stuff that happens all the time. And just like we had in the previous example, we can go through, we get the equilibrium rate constant, and then balancing the charges. And remember, we're talking about because each of these titanium vacancies is twice as powerful as each oxygen vacancy, we need twice as many oxygen vacancies as titanium vacancies to balance out all the charges. So hopefully that's clear. Now, what do we do for the electronic compensation? We start off with titanium on a titanium site, oxygen on oxygen sites, all as well. Now we pull out an oxygen vacancy, and because we've decided that this is going to be the electronic compensation version, we have to compensate for those effective plus charges with negative electrons. So we're missing an oxygen. We've got some electrons in there compensating the charge. Titanium is still on the titanium site, oxygen is still on the oxygen site, but the oxygen that used to be in that vacancy has now gone away as a gas. And so this means that we now have a PO2 dependence to this reaction. So just like we saw in the last case. So you'll recognize that almost always, there are occasional exceptions if you have something weird, like changing valence or something along those lines. Almost always, when you are electronically compensating for defects, there will end up being a PO2 dependence. Almost always, when you're ionically compensating, there's not a PO2 dependence. So that ends up being important because PO2 is something that we can adjust in the lab. We can go in the lab and change the partial pressure of oxygen in our furnace, and from that drive some of these reactions forward or backward. So that ends up being the real important reason for doing all of this, is that we want to understand how to actually tweak the properties of the materials that we care about using the kinds of knobs that we have available in the lab. And that's why representing this in terms of PO2 ends up being key. Keep in mind also that you could do the exact same thing if it's not an oxide. It's just no longer PO2. Now it would be PN2, for example. So if you have nitrogen, then this is, if you've got nitrogen vacancies, that's going to change with the partial pressure of nitrogen. The kinetics of nitride defect compensation is way slower and a lot more difficult. So that's why we usually don't end up messing with that. But it's the same approach. So any questions before we move on? Just another example of how we would write these. So I mentioned that oxygen vacancies in titania, I chose an example that really doesn't happen. And it seems strange because it's really easy to take TiO2 and heat it up in a low PO2 environment, and it becomes conductive. It turns dark, and you say, wait a minute, of course those are oxygen vacancies. Strangely enough, the defect energetics for titania often end up favoring titanium interstitials rather than oxygen vacancies. And so those titanium interstitials, so you'd end up with a titanium interstitial that would be 4+ charge. That ends up being a lower energy than oxygen vacancies. So the oxygen still goes away. The titanium doesn't volatilize because it's a cation that doesn't have a high vapor pressure, but it basically soaks into the sample and turns into an interstitial site. And it's that interstitial site that ends up being compensated by 4 electrons. Oops, one too many dots there. So that ends up being more common than oxygen vacancies. Just a random side note. So a quick thought experiment for you, or question for you. How do you tell the difference between those two? if you pull oxygen out and it turns conductive and it turned dark, and we'll talk about optical properties a bit more later, how do you know if it was oxygen vacancies or if it was titanium interstitials? That's a really hard thing to measure, but the density will change. So if you can measure the density of your sample, if you have oxygen vacancies, the volume won't change much, but the mass will be the same. You'll lose the mass of the oxygen. If you have a titanium interstitial, on the other hand, the overall density of the sample will increase because the mass is about the same, and you've shrunk the volume. So these are really difficult measurements to make practically to determine which of these species ends up dominating. But it is possible. You can go through those kinds of things. What's a little bit easier is when you're trying to compare, is it ionically compensated or is it electronically compensated? Is it this defect compensation mechanism or that one? That's what we're going to get to next is going, that's the reason that we're coming up with these thought experiments, is because then we can write down, oh, if there's a PO2 dependence, then it suggests that it's electronically compensated. If there's no PO2 dependence, then maybe it's ionically compensated. And so without knowing the thermodynamic energetic costs of each of these, we can't say right up front, but we can go in the lab and we can measure it. And if it has this PO2 dependence, then this makes the most sense. So that's the easiest way to approach it. So again, why does this matter? Those are just a couple of examples. All of the defects that we're talking about, all of the defects you can imagine will occur. You've got millions or billions of unit cells and millions or billions of formula units in your sample. All of these defects are going to happen. But the relative concentrations will depend upon how energetically favorable they are. So oxygen interstitials, yep, they definitely happen. But they usually are so high energy because the lattice is fairly close packed to squeeze in another oxygen. There's just not that many of them. So if there's 10 to the 1 of these oxygen interstitials and 10 to the 23 of titanium interstitial or electrons, free electrons that are available, or whatever the other scenario might be, then that 10 to the 23 is definitely going to dominate. And so we can ignore the low concentration. So all of these are happening all the time. It's the relative concentrations that really matter. And when we can change which one is dominant by changing the environment. So for example, PO2, that gives us a really important experimental knob to try and understand what's really happening. So Shannon, great question about the bulk density. So in that case, if you had oxygen vacancies versus titanium interstitials, in both cases, the lattice parameter is actually going to grow a little bit because, strangely enough, vacancies are larger than having an ion there. And that's just because all the other, it seems weird that having nothing takes up more space than having something. But if you think about it, that oxygen, if it's there, it has titaniums around it, and the bonds that are holding them together are going to pull those titaniums in towards that oxygen. Now you pull the oxygen out, and suddenly so if you've got titanium, oxygen, titanium, and then you get rid of that oxygen and it goes away, then these titaniums are going to shift over and be closer to the other oxygens that are around them. And the vacancy that is left behind is actually a little bit larger in volume. Conversely, shoving a titanium into an interstitial site, yes, it's going to pull stuff closer around it, but that stuff that it tries to pull around it, there's also the reason it's an interstitial site is that there's also other cations around, and those are going to get pushed away. And so an interstitial will actually make the lattice parameter grow as well. So the number of defects, the concentration of defects of those types, in both cases, you'll swell the lattice. And so there's not a hard and fast answer, if this, then this. So it depends on what the scenario is. In this case, I would measure the bulk density because the lattice parameter is actually going to increase in either case. All right. So the whole reason we do this is so that we can use relatively easy, crude, macroscopic measurements like electrical conductivity, like changing PO2, to tell us what sorts of defect compensation is happening in the material. So it's just one example, we're going back to the titania, where now we're electronically compensating for oxygen vacancies. This gives us a PO2 dependence, where we say that the concentration of electronic carriers, so the concentration of electrons, varies as PO2 to the -1/6 power. So when we change the partial pressure of oxygen, if we increase the partial pressure of oxygen, we're going to drop the number of electronic carriers as a power to the 1/6. So that all we did for that was just look at the rate constant that we had already written out, the electroneutrality condition that we had already written out, and put them together. So you can just substitute this equation in up here, and that gives you this relationship. You simplify things. We don't really care what the absolute value of that rate constant is. It doesn't matter. We are not worried about actually calculating quantitatively what's really happening from a rate constant perspective. What we care about is the proportionality. And so we can ignore the actual value of that K and just say that here, the vacancy, the oxygen vacancy concentration is proportional to PO2 to the -1/6. The number of electrons is proportional to the PO2 to the -1/6. Hopefully that makes sense. So that's what we're going to use as we move forward into actually taking advantage of all of this chemistry that we've had to review. I know Madeline's enjoying it because she was missing a chance to go back to her chemistry background. So the whole point of this is that we want to connect something that's easy to measure. So electrical conductivity, that's relatively straightforward. You stick a couple of electrodes on your sample and you apply a voltage and see how much current flows. That's reasonably simple. We can stick that in a furnace, heat it up. We can change the PO2 within that furnace, and we can make that measurement. That doesn't mean that it's simple to do with high precision, but it's definitely simpler than doing some sort of chemical analysis looking for vacancies. How do you measure something that's not there? That's really hard to do with any chemical analysis technique. But now we have a knob to be able to tell us with reasonable confidence and precision just by using a simple electrical measurement and changing temperature and PO2. And that will allow us to get not only the concentrations, but also activation energies. So that's the real value in all of this. And maybe you don't really care about the conductivity itself. The important part is that the conductivity is a proxy for whatever all those other defects are. So if we have a scenario where the number of electrons changes as a function of PO2, that is also going to tell us something about vacancies or interstitials or the other defects that are involved. And so maybe we don't care about the electrical conductivity at all, but we do care about the oxygen vacancy concentration, because oxygen vacancy concentration is going to be directly related to oxygen diffusion and the kinetics of diffusion within the sample. And the kinetics of diffusion are going to be really important for the sintering process. So if our sintering process and our densification end up being limited by the oxygen diffusion, well, an easy way to change that is to change the concentration of oxygen vacancies, because that will change the diffusion rate. Well, how do we know if it's oxygen vacancies that are really dominant in a certain scenario? We can do a quick electrical measurement after we've run through these different scenarios of what the defects in the sample might be, and say, in this regime, oxygen vacancies are going to be dominant, and I should be able to measure that by looking at electrical conductivity. It's just one example. But those are the reasons, those indirect connections, to be able to get at things that are really hard to measure themselves by using a proxy that we can connect to make something that's a bit easier to measure. So you can also go through a lot of computational methods. So this could be density functional theory, DFT. It could be just looking in JANF tables to look at what formation energies are for different defect states. All of these can provide a little bit more guidance about what is probably more or less likely in different scenarios. So you don't have to just guess and check, but at the same time, if you don't have data or if you don't have the computational tools, this write down on a notebook, what are the 5 most likely defects and what are their PO2 dependencies going to be, that can really help narrow down the options and then give you guidance moving forward. All right, so you can also, like I mentioned, you can do this for nitrides, you can do it for sulfides, you can do it for all sorts of other materials. Carbides, it's a lot harder for carbides than for nitrides when you've got more challenging kinetics associated with it. And if you've got conductive nitrides or conductive carbides, then maybe the number of free electrons doesn't really affect the conductivity enough that you can make a measurement like this that will tell you the kind of thing that you want to know. But you can still walk through the same process and go back to Shannon's question. Maybe under these scenarios that you can see that the bulk density should really change a lot, or the lattice parameter should really change a lot, something like that. Systems with carbides, nitrides, and oxides all together. Yeah, great question, Shannon. You always have the fun ones. You can go back to the mixing rules that we talked about last week at some point, to say, all right, if I apply a voltage to this sample, where's the conductivity going to be? Where is the field going to be distributed? And if you're dominated by the insulating phase rather than a conductive phase, then maybe this kind of thing would be sensitive enough to tell you something about it. But it's always going to start with sit down with a notebook and write out what are the most likely things that are going to happen. And if changing PO2 is going to make me oxidize my nitride, and that the nitride is the conductive phase within this, then maybe I can see an easy trigger for what's happening in the sample, or who knows. But yeah, the examples that I've given you here are intentionally very simple. A nice, easy, single phase material, single crystal structure, nothing complicated. As you start adding in more and more and more complications, chemistries, different reactions that can happen, then yeah, you're just gonna get more and more complex. The important thing to keep in mind, though, is that no matter how complex the system is, you are still going to be dominated by whatever the most likely defects and defect compensation mechanisms are. And so you might have 4 different phases in your sample. It's not at equilibrium. Everything is a mess, but you're still going to be, whatever your property you're looking at, electrical conductivity is the one we've focused on here. That's going to be dominated by the most conductive phase of that composite. And if you start changing things with defects, again, you're going to have all of the defect scenarios possible happening somewhere at some point, but some of those might be at really, really, really low concentrations and you can ignore them. It's going to be the majority species that are dominating. So hopefully that helps a little bit, and we will. How do you tell if the material is electronically ionically conductive when both are very low to measure, like high purity alumina? Great question. So if you're trying to measure conductivity in alumina, it's challenging to begin with. So we can go back to looking at the basic circuit models and looking at Bode plots and impedance spectroscopy. It's usually easier to measure really, really, really tiny signals in AC than in DC, because in DC you're just looking for a trickle of electrons, and the noise associated with that DC measurement may be hard to avoid and hard to get a large enough signal over that noise. In AC, there's also going to be noise, but you at least have the added tool in your toolbox of using a lock-in amplifier and saying, right at exactly this frequency, I'm expecting to see something, and so I'm going to ignore everything that doesn't sit right at that frequency, and then I can shift over to another frequency, and it makes it a little bit easier to pull out tiny signals from noisy backgrounds. So that's the kind of thing that I would use in that case. You can also change your electrodes. So we talked a little bit last time about using electrodes that don't allow a certain species through. So for example, you might, the example I used last time was sticking a platinum electrode on that would be lithium blocking, I believe. And then anything that does flow is electrons. So you could try to come up with something along those lines that blocks one species and allows another. So yttriostabilized zirconia is well known for being highly electronically insulating, but oxygen conducting. So that's one possibility. Yeah, you guys always have the fun, hard questions. I guess that's why you're here. All right, so this is the sort of why do we care about defects and defect compensations. I want to show you a visual example of this that I think will drive home the process a little bit better. And this doesn't mean that you actually have to go through this full Brouwer diagram creation to get useful information out of it. But I want to at least show you the overview so that you can see how it could be valuable. And so I guess before I jump into that, I'll try to answer Shannon's question. If a sample isn't fully dense, would we treat pores as another phase with a permittivity of air or a mixture or free space? So if they are closed pores, so this is porosity that is not accessible to the atmosphere of the furnace, then it depends on what's inside of them. So it could be free space, it could be argon, it could be oxygen, it could be air, whatever it is, the permittivity of that gas or empty space is going to be way lower than the permittivity of whatever your solid is. So yeah, to do it precisely, you would really want to know what the gas is inside of that pore, but pretending that it's completely vacuum versus nitrogen, you'll never notice the difference when you compare it to whatever the permittivity of your solid sample is, because it's going to be in the 5th decimal point. It's going to be tiny differences between nitrogen and pure vacuum. So if those pores that you're talking about are open to the atmosphere, then that becomes a little bit more difficult because there might actually be reactions that are happening just like we saw in the reactions with oxygen vacancies and oxygen gas coming and going. So if it's a non-reactive gas, like let's say you've got a alumina that you're sintering in nitrogen, and it's not a low enough PO2 that you're actually pulling oxygen out. It's just say it's air, but you've got open porosity. So there's no reason that there's any reaction between the sample and the atmosphere. Then yeah, you can treat those pores just from a volumetric fraction, like they're open space. But if there's reactions happening, then you have to deal with the energy and charges associated with those reactions as well. Hopefully that's what you're getting at, Shannon. And going back to what I mentioned last time, when a low permittivity phase ends up dominating, that's when it's in series. So if you have a sample that is a mixture, then it's almost linear. So we have the Lichtenegger mixing rules. So or Lichtenberg, it's basically almost linear. So the log mixture rule for mixed up phases. So if you've got complex 3-dimensionally connected phases, you can the low permittivity phase and the high permittivity phase are going to the overall permittivity is going to vary with the mixture of those. When they're purely in series, that's when a low permittivity phase will dominate. And so hopefully you don't have a sample that has a completely open porous layer between one electrode and the other electrode if you're making a capacitor like Shannon suggested there. But that would be the case where that porosity would totally dominate. Hopefully that was kind of clear. All right, so let's start plotting out the PO2 dependence that I just hand-wavily described on the last few equations and the last few slides. So we're going to use MgO again just because it's super simple. And we're going to look at a variety of different compensating mechanisms. So defects and then how they might be compensated. And I'm just going to do a subset of, I think, 5 of the most likely ones. I'm ignoring oxygen interstitials because we already know that those are likely to be very high energy. So we'll look at ionically compensated oxygen vacancies. So we've already done that one. It's just a Schottky defect. So we pull out an oxygen vacancy, compensate for it ionically. That's with a magnesium vacancy. Ta-da, we get a Schottky defect, and we know that that is constant with PO2 because there's no oxygen gas anywhere in that reaction. So it doesn't change with PO2. Another example, if we start with MgO and we compensate for those same oxygen vacancies, we compensate for those electronically. So now we're putting in electrons to compensate for those. We do end up with a PO2 dependence. And so this is the one that we went through earlier. And we say, the oxygen vacancy concentration is going to be directly proportional or proportional to PO2 to the -1/6 power. We keep walking through other possibilities. So if we've got a magnesium interstitial and we compensate for that ionically, a magnesium interstitial paired with a magnesium vacancy, that just gives you a Frenkel. You'll notice again, there's no PO2 dependence at all. So that one's going to be constant with PO2. If we have that same magnesium interstitial and we compensate for it electronically. So now we've got a magnesium interstitial and it comes along with 2 electrons to compensate for it. We again end up with a PO2 dependence. And so we just keep walking through these examples. Magnesium vacancy. So you notice in here, I've got oxygen vacancy, ionically and electronically compensated. Magnesium vacancy, ionically and electronically compensated. Magnesium vacancy, ionically compensated. We already covered that right there. It's just a Schottky. And so the one that I left out of the stoichiometric or a simple defect would be the oxygen interstitial. And that's because we've just said that it's highly energetic, highly costly. So from this, without actually measuring anything, without knowing anything at all about the samples, other than my baseline material is magnesium oxide, and these are the possible defects that could exist. And I know that I have to balance the sites, the charges, and the masses. These are my possibilities. And from that, I can just put together those PO2 dependencies and say, as a function of PO2, the concentration of these various different vacancies is going to vary this direction. And because those are all the exponents, in this case, all the exponents were plus and minus 1/6, I can come up with this diagram that says, when I increase the PO2, I can expect the conductivity, the electrical conductivity, to go down until I get to the point where the electrical conductivity is dominated by holes, and then it will increase as I continue to increase the partial pressure of oxygen. So this says that if I start off with a magnesium oxide material, and it's not doped, it's as pure as I can get it, it can still have these different kinds of defects. I can have magnesium interstitials, oxygen vacancies, all that kind of stuff, the ones that we went through. I've put it in the furnace and I change the PO2 at a given temperature. And so I need to put this, the reason I will heat it up is to allow the kinetics to be faster, or perhaps to increase the number of these defects that can be around. But generally, the reason we use furnaces is just for kinetics, because even for oxides, the kinetics can be really slow. I'm impatient, so I want this to happen in minutes instead of weeks. But if I let it equilibrate at a given PO2 and measure conductivity, and then change the PO2 and let it equilibrate and measure conductivity again, and just keep going through this process, I can build up one of these diagrams. And this is known as a Brouwer diagram. And so if we're measuring the conductivity, as we increase PO2, we're going to see it decrease and then turn around and go back up. And that just tells us that down here, it's electrons that are dominating the conductivity, and up here, it's holes. If I had a high enough mobility material, I could also do a Hall measurement where I apply a magnetic field and measure the conductivity, and that will tell me relative to the magnetic field whether it's electrons or holes. But maybe I have access to a Hall system, maybe I don't. But the real value in this one is that we can now tweak the behavior of the sample by changing the environment that it's in. And this doesn't just tell us conductivity, because frankly, we might not care about conductivity, but maybe we care about oxygen vacancy concentrations. Maybe we care about magnesium vacancy concentrations. And that's the important part that we get out of this these kinds of diagrams, is that relationship. And just as a reminder, this magnesium vacancies dominating at high PO2. Remember, that does not mean that I'm actually boiling out magnesium. It means if I've got this lattice and I'm at a really high PO2, I'm actually adsorbing oxygen onto the surface. And the equivalent is having a magnesium vacancy because there's no extra magnesium to make up for having that extra oxygen hanging out there. And we just refer to that as a magnesium vacancy. Hopefully that makes sense. So any further questions on these kinds of scenarios? So in this case, you'll notice I don't have any numbers on here. So I haven't bothered to write in what the actual concentration of these various defects might be. I haven't put any numbers on the PO2. So what is the PO2 where this crossover happens? I don't know. It varies with the system, and it varies with basically all of the energetics that we've been talking about. I haven't actually made a single measurement to be able to create this plot. This is entirely if this, then that. So that's the other part of the value for it, is that I can do all of this before I even go in the lab and make a single measurement. I can know if these are the dominant defects, this is the kind of response that I'm going to see. And when I talk about high PO2 versus low PO2, it is totally relative based on whatever the energetics of those particular defects are for this sample. So for magnesium oxide, I know that it really doesn't want to lose oxygen. So the PO2, to get a bunch of oxygen vacancies, this low PO2 region is going to be very, very low partial pressure of oxygen. In other materials, maybe losing an oxygen is relatively low energy. And so this crossover might happen at atmosphere, at standard atmosphere. Cobalt oxide does that. It switches between N and P type right around 20% oxygen. So relatively high PO2. So there are a bunch of different examples of this. So if you hear of certain materials being intrinsically N-type or P-type, this is the kind of thing that it's referring to. Is that what are the dominant charge carriers? And generally that's because what are the defects that are in there and how are they compensated? So this example is just showing you two regions. You can imagine there could be a possibility where any of these defects and compensating mechanisms that we've talked about, any of them could end up dominating under certain scenarios. So another example is maybe I have a system where the oxygen vacancies dominate at really low temperature or really low PO2s. The magnesium vacancies dominate at really high PO2s, but in between there's a region where the lowest energy defect pair is actually Schottky. So what does that look? You can create these Brauer diagrams that would cover any sort of scenarios that you want to. And so it makes sense that if you get to a low enough PO2, whatever that arbitrary PO2 is, that something like oxygen vacancies will dominate. But depending on the system, there might be a region where Schottky dominates, or Frenkel dominates, or that electron hole pair that we talked about from just the photovoltaic type reaction might dominate. And so you can create these Brauer diagrams, what if scenarios for any of these. Then you go in the lab and make your measurements and compare to the what if scenarios you put together and say, this one matches. It makes a lot of sense that this is what's happening. So if the atmosphere is inert, the word inert is the active one there. So what do you mean by inert? So it might be an atmosphere like pure argon, where the argon gas that you're putting in the atmosphere isn't actually interacting with your sample. But if your sample is an oxide, if you get to a high enough temperature, the PO2 is not going to be, so the PO2 is going to be low because you've got oxygen or got argon around. And so you can still lose oxygen from your oxide sample in an inert, non-reactive environment just because that inert non-reacting environment doesn't have oxygen. And so you're going to essentially boil off oxygen from your sample surface. That's why the partial pressures are the parts that matter rather than the absolute pressure. So a lot of times we don't necessarily need to run hydrogen or carbon monoxide into our furnace to pull oxygen out, to lose oxygen, to create oxygen vacancies, to get to low PO2s. We can do it just with nitrogen or just with argon, because the partial pressure is the part that really dominates how those individual species in your sample are going to react. And that's another piece to keep in mind. I mentioned earlier on that we have to remember that all of these reactions, the quantitative aspect of the reaction assumes that the defects are dilute and non-interacting. Qualitatively, you're still going to get the same kinds of trends. You just might have to tweak little parameters here and there to get them quantitative if they are interacting, and that's relatively straightforward if you know information about your system. But yeah, keep in mind that it's the partial pressure of the atmosphere that really matters. All right, and so if I'm not going to go through the example in detail here, but I will point out if you're interested in this and if you want to see more, that defects.pdf that I put on the Dropbox goes into more detail about how to calculate the concentrations of these minority species. So you'll notice that when the Schottky reaction is the dominant defect scenario, we still have changes in the concentration of electrons. So the concentration of electrons drop dramatically even while that Schottky defect is dominant, and the concentration of holes increase dramatically across that Schottky barrier. That is non-intuitive, because you'll notice that equation doesn't have anything in it about electrons. It doesn't have anything in it about holes, and yet these species are changing concentration dramatically. And so that comes down to the fact that all of these defect reactions that can happen in a sample are happening to some extent, all of them. It's just a matter of what are the relative concentrations. And so if you were to, for example, measure the electrical conductivity of this sample that had this kind of a Brouwer diagram, if you're measuring the electronic conductivity, and going back to Jan's question, how do you know if it's electrons moving or ions moving? So you could do it by looking at mobility. You can do it with blocking electrodes. We're gonna make the assumption right now that we know that we're only measuring electron conductors, not ions. Well, in that case, the conductivity that goes along with this sample is going to decrease here. And then even while the Schottky, even in this region where the Schottky reaction is dominant, we're going to see a strong drop in the electrical conductivity. And then it's going to go back up and continue along as the holes conduct. And so even though the dominant species in this region are the Schottky vacancy pairs, the conductivity is going to track the electrical conductivity, is going to track the electronic species concentrations, and those change significantly while that Schottky is the dominant defect. So that can end up being super important as well. And it basically just comes down to when these are happening, when these reactions that we've drawn out, when they're happening, we know that they're all happening simultaneously. And we know that in one region, let's say over in this region, we've assumed that this is the only thing that matters. And then in this region, we pretend like this is the only thing that matters. But then when we shove them together, we have to recognize that at that boundary, they're all happening at roughly equal concentrations. And so we have to put all of these different scenarios together. And it ends up being a little more tedious, but it's really just substituting equations over and over again. And so all that does is say, while this Schottky in this example, a reaction is dominating, these other reactions are also happening in the background. They're just at lower concentrations. But if it's those lower concentration electrons or holes, for example, are what we're measuring, then it still ends up being important. And so because the Schottky reaction, when that's dominant, is going to pin the concentration of oxygen vacancies, for example, That's why you end up getting a change in the response of the alternate species, because all of the positives have to end up equaling all the negatives because the material has to still be electrically neutral. So hopefully that's at least clear enough that you have questions, or clear enough that you can look through the document and get a bit more detail along the way. Happy to go into more detail about that, but didn't want people to fall asleep if this wasn't their bag. So if you do have any questions, please jump in and ask. Otherwise, we are going to wrap up the point defect portion and then move on to a few more topics. And we can always come back to this if people are interested. So keep in mind, real samples, always more complex than these simple examples. So Shannon's already given us one example in her question about 3 different, wildly different phases that are going to be present. How is that going to affect things? Well, we're going to have to break it down into each individual component and see how each of those are going to react, and then look at interfaces between them. The examples I've given you here are really just the baseline starting point. So you're always going to have unintended impurities. So this can tell you it's really important to know where your starting materials came from. So what kind of a mine produced this titania, or this silica, or this alumina, or whatever it is. The parts per million, or maybe even parts per billion impurities that come from whatever the starting material was, may end up dominating your properties, and you may not even know it's there. So these kinds of measurements can be really powerful for identifying, if not the exact species, then at least the effects of those unknown impurities. You might be able to determine that there's something there, even if you couldn't find it chemically, and then deal with it that way. We made the assumption up front for this treatment that the defects are non-interacting. That's often not the case, but this can still give us a really good starting point to work out what kinds of relationships we're going to see. However, if we get defect complexes and interactions, so maybe you've got an oxygen vacancy and a lead vacancy that really want to hang out together and end up binding and create a complex that's really hard to break. That can slow down the kinetics, that can cause other interferences that might be difficult to recognize. I mentioned valence changes. So when we were talking about titanium, I mentioned that you could go from a titanium 4+ to a titanium 3+. And in that case, you can go through the exact same sort of process that we did and just call that titanium 3+ on a titanium 4+, one of your defects, and go through and see how that's compensated with an electron, with a hole, depending on what the species are. So we'll talk a little bit about polaron hopping later on, but that's an example where you can have low mobility electronic contribution to conductivity because of hopping from those different valent cations. You also, all of the examples that I gave you, we pretended like it was a completely infinite, perfect lattice, right? There's no grain boundaries around. There's no electrode interfaces. There's no reactions that we have to deal with other than reacting with the atmosphere, with oxygen coming or going. We were avoiding any phase segregation. So I talked a little bit when we were looking at the very first example of aluminum oxide doping magnesia, about you could actually drive the alumina to precipitate out using the Chatelier's principle, going back and forth with that reaction. Those kinds of reactions are possible, and that kind of control is possible. These can give you a guide to think about how you might go about that. And these last ones are also important. Everything that we just went through, it's assuming equilibrium, which means it doesn't change with time. So we're assuming that you're at a high enough temperature that you make this electrical measurement, you change the PO2, you make another electrical measurement, change the PO2 again, that you're allowing it to get to equilibrium at each point. But keep in mind, if you're doing these kinds of measurements, maybe your microstructure is actually ripening, maybe your grains are growing. If that's the case, you're probably at a high enough temperature that you're complicating things unnecessarily. So ideally, you're doing these measurements at a low enough temperature that the microstructure isn't changing. But maybe the kinetics are so convoluted and so slow that you have to increase the temperature to get that, but then you have to recognize that you've got additional stuff happening beyond just the assumed equilibrium. And so you might have some sort of aging, you might have some ripening of microstructure. Keep those in mind. And again, all of this assumes so far that you're at equilibrium or at least very close to it. So kinetics are important. Kinetics are always important, whether we like it or not. And then finally, I don't care if you ever make a Brauer diagram. This is still a valuable approach to thinking about how defects interact in your sample and what might happen if you have this kind of impurity, or if you have that kind of a dopant, or if you sinter in this kind of an atmosphere. You can go through these kinds of thought processes to identify, oh, well, if I really need, I don't want oxygen vacancies because those are going to lead to electrons, or potentially lead to electrons. Therefore, I don't want to sinter in this low PO2 atmosphere because that will give me oxygen vacancies, and I don't want electrons conducting. Maybe your system doesn't compensate in that way, and it's no big deal. But that's the kind of thought process that I want people to be able to go through. And remember, it's not just about the conductivity. It is about the connecting that thing that you can measure easily, the conductivity, with what are the defects. So the relationship of vacancies and interstitials and those kinds of species to sintering kinetics is a really underappreciated aspect of this approach. So if you know, or if you want to find out what the rate limiting step is in densification or in grain growth or whatever diffusion process is happening in your sample, this can be one way to approach that. And this can also tell you why doping with a certain material might change your sintering behavior. So adding magnesium oxide to alumina is one example. That one's wildly complicated, that it's taken people a century to figure out. But in other simple versions, if you put in a species that's going to promote oxygen vacancies, for example, in a scenario where oxygen diffusion is the rate limiting step, then you can suddenly sinter a lot faster because you've sped up that slow diffusing species. That's why we think about point defects from this perspective. All right. So another homework, and again, this is really just to make you think about what we're doing. If you want to email it to me, great. If you don't, no problem at all. But I want you to think through what kinds of defects are in your system. So maybe it's impurities that you really hope aren't there, but you don't really know for sure. Maybe you're intentionally adding dopants that are a different valence. Whatever it is, what would be important for your systems, and are they intentionally there? Are they unintentionally there? Is there some sort of unintended consequence of putting this species in there? Who knows? What happens if you change raw materials? So you've been buying this precursor from Acme Powder Company for 20 years, and suddenly your product doesn't work anymore. You're still buying the same stuff from Acme, but they changed the product number because they made it more pure and they think that's a better thing. Well, those impurities that they just got rid of, your entire system was built around those being there. And now you don't know what you're missing. And you have to go through this kind of a process to figure out what did your supplier just improve that screwed up your process. Those are some examples of what I want you to think about with this. All right, so we've got a few more minutes. We are not going to finish this ceramic processing overview, and we could have an entire course on ceramic processing. So this is really a high-level overview, just scratching the surface. But I wanted to quickly go through things just to set the stage for a few other pieces later on, and to hopefully connect what we were just talking about from crystal symmetry earlier on to point defects right now to what we're going to get to right after this, which is piezoferroelectric and other more emergent properties. So we're going to focus on how the processing impacts defects and electrical properties in these kinds of materials. All right, so in my opinion, ceramic processing is really just making stuff. So we start with a powder, we start with a solution, we start with a vapor, whatever it is, and then we turn it into a product. And all of the details of how to go from that raw material into the product that has the properties that we want, that's ceramic processing. And the difficulties of that process, that's why we all have jobs. Because not just any Joe Schmo off the street can do this, because ceramics are really sensitive to the way that they are made. So since we're going to focus on electrical properties, I'm just going to start off with a few reminders, and that'll keep us, I guess, focused around that. So electrical and optical properties are really, really sensitive. They can be sensitive to parts per million or even lower levels of impurities. And from an optical perspective, that's because of interactions with photons, and you can change absorption, you can change color, you can change all sorts of things with very tiny impurity levels. Electrically, it's the same sort of scenario. So because the electrical conductivity changes with the number of carriers, and if we change those number of carriers by orders of magnitude, we change the conductivity by orders of magnitude. And because there are 10 to the 23 atoms per cubic centimeter or something on the order of that for everything, if we change by a part per million the chemistry, then we can change by 10 to the 17 the number of carriers in that cubic centimeter. So that's just to give you some perspective of why these matter so much. All right, so when we're making these things, generically, we're gonna start with some sort of raw material. This is built on a powder-based process, but we're gonna mix it, calcine it, break it up. So a combination is just making the big rocks back down into little rocks. And then we're gonna go through some additives and forming and sintering, all that kind of stuff. I'm not gonna go through all of the details on this, but this is the way that I like to think about ceramic processing in a generic sense. Again, I'm just going to focus on a couple of examples that are related to the electrical behavior. So as I mentioned just a couple of minutes ago, don't forget that your raw materials came from somewhere. And getting to parts per million level of impurity or better is expensive. It's difficult. It may not be essential for 90% of products or 99% of products, but your particular product happens to be really sensitive to this kind of impurity and this particular raw material, and so you have to know that it's there. So, for example, if you're using alumina that comes from the Bayer process, it had a lot of sodium and silica in there. Usually, those are fairly easy to get rid of, but not always. Titania is always contaminated with zirconia, with hafnium, with iron. Zirconium and hafnium are really, really hard to separate from one another. Tantalum, always very hard to separate from niobium. These are just simple examples. And then one that has burned me a few times, hydrogen and hydroxides, and to a lesser extent, carbonates. We almost never measure them. We certainly rarely measure them and report them effectively. I will use magnesium oxide as another example, because we just went through an hour of looking at magnesium oxide as a matrix for our defect compensations. You expose magnesium oxide or barium oxide or strontium oxide, any of the alkaline earth in particular, others do this as well. Expose those to air, they are going to form a surface carbonate, whether you like it or not. And so if you grab a bottle of magnesium oxide off of the shelf, you should the first thing you should do is go do some DSC or TGA on it, because you don't know how much water it picked up by sitting there and soaking up humidity. You don't know how much carbon dioxide that it absorbed and became magnesium carbonate or barium carbonate or whatever it is. So a simple excuse or approach to that is just buy the carbonate. It's probably cheaper anyway than buying the oxide, and then at least you know what you're starting with. Still have to deal with the humidity aspect, but I point out hydrogen and hydroxides in particular because they can be difficult to quantify. So not a lot of chemical analyses that we do on a regular basis will pick up extra hydrogen protons that happen to be hanging out. Only a handful of them will pick up hydroxides. So if you do FTIR, sure. But is that surface water that you can dry off at 200 C, or is it actually chemically bound and you have to go to 400 or 500 or 600 C? It's harder to tell. So just a reminder that know what you're starting with, because it's going to matter, and you don't want to find out after the fact that you really should have measured the thing you started with. As you're going through all of these steps along the way, mixing, calcining, and milling, it's really easy to assume that you didn't screw up your product, you didn't screw up your powder. But your powders are abrasive. They're ceramics. You're probably using, you're either using other ceramics as the milling media and as the mills, or you're using polymers that are getting abraded a little bit. Big deal if you get a little bit of your Nalgene bottle mixed in with your powder, it's just going to burn out. But what if you're using steel? You just contaminated your sample with iron and chromium. Keep those in mind along the way. That applies during the mixing process, that applies during the forming process. You can very easily get part of your dye into your sample as you're pressing apart in a stainless steel die, these kinds of things. And gravity always wins. This is the same advice I give to anyone learning to ski. Gravity always wins. Don't fight it. Just know that it's going to happen and deal with it. So if there's a chance for density separation, it will happen, whether that's milling, whether that's drying, whatever it is. Your powders are just naturally going to separate based on density and based on particle size. And if you pretend that it doesn't happen, it will probably come back to bite you. If you recognize it, it's relatively easy to deal with. And this last one is one that is really important, because as Shannon reminded us, the distribution of different phases in a material can have a big impact on the electrical properties. And calcination, it's really easy when you write down an equation on paper that says barium carbonate plus titanium plus strontium carbonate equals BST. But it's never that easy in process. And even though that's a system that has been studied to death for 80 years, Wolfgang and Jacob recently published a couple of different independent papers on the BST system and how the calcination process is not as straightforward as everybody thinks it is. So in situ diffraction showing when these different species react with one another has a big impact on the resulting phases and the resulting chemical distribution and therefore the resulting properties. And so just keep these kinds of things in mind because it's going to end up mattering. And as an example of this, I will point to some work that I did a little over a decade ago, where according to all of the ex situ X-ray diffraction that we did, so we mixed barium titanate plus bismuth zinc titanate. We were making these capacitors that were relatively stable with temperature and with electric field. But every time we would calcine these things, we would end up with this Oreo cookie looking layer within the powders. And we said, there is something wacky going on here. But we would throw these powders in the X-ray diffractometer at room temperature, and they always look the same. When we did chemical analysis, we couldn't see any differences. What the heck is going on in this? But you can tell optically. And remember, optical properties can be really, really, really sensitive. Optically, there's obviously some segregation happening here. And so we ended up doing in situ diffraction along the way and noticed that we were, strangely enough, forming this weird barium bismuth oxide intermediate phase where the bismuth is half 3+ and half 5+, just completely unexpected. But these complex reactions where we're just taking two perovskites and mixing them together and heating them up, it's never that simple because atoms have to diffuse and they can only go so far, and they're going to happily react with whatever's nearby rather than whatever reaction that you threw down on a piece of paper. And so you can end up with a lot more complexity along the way than you ever expected. And maybe you give it enough time that you end up getting somewhere near equilibrium and all is well. But maybe you don't, and you don't necessarily know the kinetics of the process going into it. So this is just one embarrassing example from my past where we thought things were simple, and then we had to learn the hard way that no, there's a lot more going on than we ever wanted to admit. But eventually we figured out, once we saw all this happening, we were able to back up and figure out how to make these samples homogeneous along the way. Or so we thought. Come back to that example in another minute. The additives that you're putting, so that was for the calcination step. The additives that you're putting in, binders, dispersants, all this kind of stuff, they are never as pure as you want them to be. In particular, a lot of people like to use Darban because it is a spectacular dispersant. Keep in mind, though, some Darban products are the sodium salts. Some Darban products are the ammonium salts. I believe Darban C is the sodium. Darban 811 and 821, at least the old names, were the ammonium salts. Double check that before you believe me. But they're the salts of polyacrylic acid. And if you use the sodium salt, great. You just doped your sample with sodium. If that doesn't affect your properties, no big deal. But if you're making a barium titanate capacitor that's really sensitive to the sodium concentration, maybe your dispersant is the reason that this batch is way different than that batch. So keep in mind that whatever you're throwing in your dispersant in your binder is going to end up in your sample. And that's why the ammonium version is nice, because it goes away as a gas, but then you've got to deal with ammonia. Binder removal is never as simple as we want it to be. So there's a lot of carbon in most of these binders, and it's the local PO2 that matters when you're doing burnout. So you may say, oh, I did this in air, no problem, it got rid of all the carbon, big deal. But in the center of your sample, where in order to react with that binder, that carbon in that binder, the oxygen has to diffuse all the way in from the outside of your sample, react, and then the CO2 has to diffuse all the way back out. Maybe you didn't give it enough time. And it's the local PO2 that matters. So if the binder, you've heated it up and it's turned to graphite and reduced locally your sample, and it's taken oxygen from your sample rather than from the atmosphere, and left you behind with a reduced cation, titanium that turned to a 3+, or lead that turned into metallic lead, who knows what. Keep in mind that it's that local PO2 that really matters, because each atom has no idea what's going on in the furnace overall. It only knows what's in its nearest neighbor. And so that's a key part that has bitten people in the past. And every single time your powder touches something, there's a potential for it to react. So I use this last one as an example where you might lower the pH to help disperse your powder within water, and then you moved on. You're now pressing your sample in a die, but that low pH is increasing the corrosion of your stainless steel die, or whatever the scenario is. Every single thing that your powder touches is going to interact in some way. And again, the electrical and optical properties can be super, super sensitive to those. So keep that in mind. Forming, similar to what we just mentioned, but the sintering is where a lot of the magic happens. And just keep in mind that during sintering, no vapor pressures are negligible. So we always pretend as if they are. We're lazy and assume that the furnace is a magical black box that we throw it in and it gives us heat and nothing else. Except every time you stick your sample in a hot furnace, your sample is the cold finger. Your sample is the coldest thing around for a while. So anything else that has ever been in that furnace that volatilized and collected in the refractories of that furnace, that now has a possibility of landing on your sample and condensing because your sample is colder than everything around it. The elements themselves, the elements are hot. Moly disilicide, it's going to slowly boil off. Moly and silicon, silicon carbide, blow bar. Ideally, it's got a nice protective SiO2 surface on there, but even that is not perfect. It's the vapor pressure is never zero. The crucibles, we use alumina crucibles, zirconia crucibles, because they're not reactive. Well, they're not reactive. They're just less reactive than the other options. And so a great example is from Tadej Riac from Josef Stefan Institute. For years, people have been studying bismuth ferrite and been struggling with getting single phase bismuth ferrite to form because it always wants to form iron rich secondary phase that people just could not get rid of no matter what they did. And Tadej went through some very precise experiments and found out that it was because everyone was reacting their bismuth ferrite in alumina crucibles that they were seeing this. And if you don't use an alumina crucible, no problem. You don't form this other intermediate phase that was at such low concentrations that nobody was ever seeing it in X-ray, but it dominated the phase progression from there on out. So those are just some examples. This also applies to the seasoning of lead furnaces. So anybody that's ever sintered PZT or PMNPT or any of the others, you know that the first time you throw your sample into a brand new furnace, it's not going to work. And that's because lead and lead oxide are very volatile. And you have to end up eventually coming to some sort of equilibrium so that your sample is not just contributing all of its lead to the furnace. The furnace is balancing that by giving you some of the old lead that it absorbed previously. These are just a couple of examples. And as we talked about from the very beginning of this discussion about defects, your sample's never going to reach equilibrium. We pretend like it does, but it's probably not. And then when you cool it down, you've just locked in whatever approximation of equilibrium you were able to reach. So maybe that's during the cooling process, maybe it's whatever it was when you're at the highest temperature. But just keep in mind that you're not at equilibrium and you're probably measuring something that's not even representative of the root temperature where you're measuring it, but probably the processing history. So with all of that in mind, I just wanted to show you one last example of the earlier barium titanate, bismuth zinc titanate samples that we were making. And these are two examples of samples that were, as far as we could tell, very, very close to identical, but very slight differences in defect chemistry. And those very slight differences in the defect chemistry, in this case, it was controlling the titanium to barium or bismuth ratio. Very small differences made huge differences in the chemical distribution. So these are backscatter SEM images. And so the higher the brighter the color, the more the bismuth, the higher the relative atomic number. So this sample ends up giving you just garbage electrically. This one was absolutely beautiful electrically, and it comes down to whether you have discrete second phases or if things are relatively graded. And that change in microstructure and change in grain size and change in distribution of elements was all about the defect chemistry, changing the intermediate phases along the way and the diffusion rates of different species. And it was tiny amounts of cation ratios that made all the difference for those microstructure developments and the resulting properties. So with that, we'll come back to wrapping up processing and jump into fun ferroelectric behavior on Thursday. I need to warn you, on Thursday, I'm going to have to jump out about 10 minutes early, but we'll get to a nice stopping point for that one, and just giving you a heads up that we'll start on time, but we'll end just a little bit early on Thursday. So any other questions, please shoot me an email, drop something in chat. Otherwise, I will see everybody in a couple of days. Thanks.